So we're now doing the ball on the top of the ramp question, which is quite interesting. First off, we use energy. This is the energy equation we talked about many times. Now on the top, there's staying stationary. So it's PE, aka potential energy. And we don't actually know if it's slipping or not, but I told you it's slipping basically. So I told you there's no slipping, no slipping. So we can actually just solve it right now. But in the next section, part B, we'll figure out how we can determine if they're slipping or not. So first thing I need to know is MGH. That MGH is because it's just gravity up over here. Because you just drop it, there's no movement. And then the translational is because the center of rotation is moving along here. This rotation is because it's rotating along this way. And if you want to know, and I think it's actually this way, but if you want to know why in the pendulum there's only rotation, it's because you're moving along the pivot point, the rotational axis. This is not moving transitionally. So those are the things I need to talk to you about. Because we do that over here later on where we do all potential, we do omega over here. Where is it? Over here, where we don't use translational because the pivot is not moving along. That's an important thing to note. That confuses people, but I think you get it now. So there's the translational kinetic and rotational kinetic. Maybe I should write that down later on. Probably should. No slip kinetics, which means this is true because this is just a ball and this is the symbolistic velocity r. So we now just have basically put this along here and then simplify it to get v. V isolate, you know algebra. You should know algebra. There's no reason for you to not know algebra at this point. Anyway, let's analyze one of those balls over here. So if you notice here, there's an F normal force. F normal force is over here, but that really doesn't matter for the rotational purposes, but it does matter for the force on the y direction, but we're not dealing with the force on the right direction. So we're using that to figure out friction over here. With that friction, we can get this format over here. Using another one of those kinetic equations, we can get the torque or moment around here because there's only one moment to the axis, which is why this is true. After that, a little bit more algebra gives you acceleration in the x direction, which is this way. And now with that, you just plug back into the friction equation because we have our equation related to acceleration in x direction, which gets you this. And then we plug into the original equation to get you the kinetic coefficient of friction.